Thanks, everybody, for coming to my talk. I know it's a hard time after lunch. I'll try and keep you guys awake. Yeah, so first question is ready for you. Who knows in which movies we had these two artifacts?
Indiana Jones.
Yes, well done. Wow, that was quick. We should have done the quiz like Mirko did earlier. Yes, Indiana Jones and the Last Crusade. Awesome. So, a little introduction about me. My name is Fabio Tiriticco, and I work mainly as a Scala Akka consultant. On the internet, I'm Ticofab pretty much everywhere. And as introduced, I come from Italy, originally from Rome, but I've been living in the Netherlands for the past 12 years. So actually, I would like to say I'm really happy to be here, because it's the first time I speak at a conference in Italy. So really big thanks to the organizer for having me. Quick fun facts about me. I once cycled from Amsterdam to my hometown in Rome. And second fun fact, I had a side business in the Netherlands selling these Italian meat skewers called arrosticini. I don't do that anymore, but that's me with my partner during some event in the street. But more close to this conference, I also run the Reactive Amsterdam meetup. Started about 3 years ago. We grew a lot. We're about 17,000 members now. And we talk about everything reactive. So reactive programming, but reactive system designs, basically anything you can put the word reactive in front of. Before we start the actual talk, a few notes. This was meant to be a talk with another guy, but my co-speaker is on holiday. And he is the actual Kubernetes expert. So I am covering for him, and I know some about Kubernetes. Let's see how far I get. So that's it. Then, only relevant concepts are introduced. So you could talk about Kubernetes for 3 days in a row, or Akka actors, same thing. So I'm just going to narrow it down. And then third, the code that you see on the slides, it's not much, but it won't compile. So the real deal will be on GitHub. And I've done this to keep it really focused on what I need to introduce. So most of my talk start by mentioning the Reactive Manifesto, written a few years ago by those awesome guys. The best wording about it I have heard from Jamie Allen at a conference last spring. We build elastic and resilient systems via message-driven architectures in order to give users a responsive experience. That's the ultimate goal, responsiveness. And today, of all these traits, we're going to focus on elasticity. Elasticity, especially in today's cloud environments, means really be able to react to maybe an increase, a spike in load, but also a decrease in load. You want to use just the right amount that you need, especially not more, because you're going to pay for those instances on EC2 or whatever, and they're expensive. So you really basically just want to use the right amount. Now, how does Akka build up to achieve these things? The building blocks of Akka are actors. They were introduced already in the talk before lunch, so I'm just going to go very quickly through this. Actors are isolated islands of computation. Really is a basic unit of computation in Akka. An actor contains state and behavior logic. So for instance, in this case, each actor has a name: Bob, Tim, and Joe. Are there Bob, Tims, or Joes in this audience? No. Well, they are on the screen. What's special about them, one of the things, is that if you want to know each other's name, for instance, want to know what's the name of actor 2, you cannot do a thing like that. So you won't have a reference to it and invoke a method on it like we would do on a classic Java code. Instead, an actor has an addressable mailbox to receive and send messages. So let's say Bob wants to know what's the name of actor 3. The only way he can do it is by sending him a message. What is your name? To which actor 3, Joe, will respond, my name is Joe. And to me, the power of this is that this models reality so much closer. If you want to know how old I am, you're not going to read some variable in my head and like, dot get age in my head. You're going to ask me, what's your age? And I will respond, 21. What are you laughing about? This talk is about this research that we've done, and so as a personal story, I'd like to go back to the first moment where I first interacted with reactive systems and with the reactive world. A few years ago, it was 2013 actually, I had this idea for a company. I wanted to enable gesture communication across devices. So pinch from one screen to another, or swipe across the screens. And when you have such an idea, the only thing you can do is go ahead and do it. So we did this, and there's a couple of videos I want to show you from back then, something that you could do with this engine that I built. You could display images that match on two screens. Or another obvious case, before WhatsApp really came, you could share pictures from one phone to another. You can see the phones are not really recent models. But there you go. The next one is probably my favorite. Once you established a connection between two phones, then you have these two shapes. You can just pass them like this one to another. And so we built a little company around this. We were with three, 4 people. We had one paying customer that I'm really, really proud of, but most of the reactions were like, that's cute. But exactly what problem does it solve? Yes, so that's why this company doesn't exist anymore. But if you have great ideas that this technology can solve, please come talk to me after. And because it's 2018, of course, we will build it on the blockchain. But go back to my implementation. This engine had a few requirements. So if you look at these 3 cases, they need to manage many devices concurrently. You have many millions of phones connected at the same time. Hold state for each device. So each device has a location, has maybe, for instance, in the 3rd case, which device has the blue square, things like that. Deal with short device life cycles, because devices appear and disappear. Matches are created and destroyed. And another one is to have a fast bidirectional channel between devices to exchange information, such as, yes, maybe the picture bytes, or information such as who has which shape, things like that. So Akka and its actor model really looked like the perfect use case for this. So a possible architecture would be something like this. Let's say you have these 4 phones that connected to your server. And then let's say you have one actor. So each of them is an actor. Then you have one actor that knows about them all and is able to decide who has matched with each other. So at some point, this matcher actor might send a message to phone 1, say, hey, you've matched with phone 4, and this is the address of phone 4. Then it would send a message to phone 4, saying, you matched with phone 1. And the power of actors is that once they know this, they can send messages to each other directly without having, hash tables or, lookup tables or whatever. They just talk to each other directly using their addresses. Now, you already maybe see where I'm going. What if 10 million phones connect at the same time? They're too many to be hosted on one single JVM. So you will need to distribute your application somehow. And we're going to look at how we can do it in a second. But first, another concept mentioned by the previous talk, the concept of location transparency. Just state what this concept is. Let's say my co-speaker is in New York. Actually, I think it's in Indonesia, but let's say he's in New York. And for him, it doesn't matter if I am in the same building with him, or in Siberia, or in Australia. All he needs to know to send me an email is my email address. And that's exactly what happens at an actor level as well. If Bob wants to send a message to Tim, Bob doesn't know if the actor runs on the same JVM or on another node. And in Scala and Akka, you do this with team address, and then exclamation mark, and then you send it your message. So now, how am I going to test this thing of elasticity and location transparency? Created a little test system right there, where we'll have one source, which is an actor, which will emit jobs to carry, and then there will be a master actor receiving those jobs and forwarding to some workers. So obviously here, the more workers we have, the more jobs we can process at the same time. In the demo that you're going to see, there is also a little HTTP/WebSocket server that I use to change the rate of emission of the jobs, but also to monitor what's going on. We'll see it in a minute. Let's give a quick look at the worker. It's very, very simple. A worker actor receives the job and simulates some intensive work, and then sends a message back to the master saying job completed. And this is very crucial. The fact that workers tell us when they're done lets us know how much we are processing at any given moment. And this might help the master to detect situations, for instance, where we have too little power. There's too much work coming. We don't have enough power to carry it out in time. Well, this is where Kubernetes starts to creep in. To face this situation, we introduced a scaling controller. A scaling controller is yet another actor to which we can send a message, add a node, please. Then another worker node will magically spin up, and then the master is now able to send message, to send jobs to this new worker as well. Situation is solved, but then at some point, maybe we have a situation where now there's too much power. And then again, please, scaling controller, remove a node for me. A worker will go away, and situation is restored, just the right amount. I believe the Swedish word for that is lagom. Is it? Just the right amount. Okay, great. We have now a couple of issues. First, how do we distribute this? And here, again, like the previous talk, Akka cluster to the rescue. Akka cluster lets you choose a node, which will be the seed node, to which all other nodes can connect. And this will create basically a sort of mesh networks where all these nodes can talk to each other. And then here, we're talking about nodes. So in our case, JVMs. Inside each node, there will be your actors doing their thing. And there's this basic membership service that Akka cluster gives you. So each node at any given moment has a state, which can be maybe a node is joining, a node is up, a node is leaving or is unreachable, and so forth. Important thing to note for us, that we're looking at Kubernetes from the distance now, nodes need to know the address of the seed. Each node needs to join the seed, which is why in practice you will want to have more seed nodes, but for this thing we're just going to stick to one. And so how does it happen to move workers on different nodes? First situation, we have a single JVM where everything runs, but then we're going to split it into one JVM, which will be the seed node and runs the master and the job source. And then each node will get its own JVM. For simplicity, we're going to keep one worker per one node. And so here we are. First issue solved. Now, second issue, how to spin up and spin down nodes. And here you got it. Docker and Kubernetes come into play. I'm not going to mention anything about Docker. I'm sure you all know what it does. But why Kubernetes? Kubernetes is this container orchestrator engine. And I chose to go with it because, yeah, first it solves my problem of spinning up and down nodes, but also it offers some kind of resilience. If a node crashes, it will restart it. Then there's mainstream adoption. Everybody's doing it, everybody's talking about it. Cloud providers, many of them, Google, Amazon, Azure. And there are some APIs, which is what we're going to use right now. So our scaling controller there, which does the magic of spinning up and down nodes, now becomes a Kubernetes controller. And if we look at how it's done, it's really, really simple. It's a guy, it's an actor, that receives messages of the kind of add node or remove node. Then what comes later, we're going to give a look, is API, Kubernetes API stuff. And how does the master ask for changes? Well, simply sends a add node or remove node message to the Kubernetes controller. How does this setup look when you put it on Kubernetes? This is what we have described so far at the application level. You have that one JVM is going to be the seed, and then you have more JVMs, they're going to be our disposable nodes. In Kubernetes, you will put each JVM in a pod, where a pod is really the basic unit of computation in Kubernetes, is let's say your process run into a pod. Below pod, they are managed by these categorical controllers, such as deployment is one of the controllers. And you can see controllers like the waiter at a restaurant. You write him a menu of what you would like. The deployment takes it, goes back into the kitchen, and makes sure that you get it. So for instance, you could ask the controller, hey, I want to have 4 nodes, 4 worker nodes, and the controller will make that happen for you. There's yet another category, services. Services are abstractions which defines a logical set of pods and how you can access them. In human words, I need a DNS because you want that the seed node has a fixed address. You don't want to have it a changing IP address because otherwise the worker nodes wouldn't know how to join the cluster. So we need to give it a DNS, so a name that will stay always the same, even if the underlying IP changes. And then I need some HTTP forwarding thing. It will be a load balancer for our HTTP and WebSocket server. Right, so this is basically what it looks like. Now let's check a little code and maybe record a demo. Let's see what it looks like. So, time for some code. Yeah, read it, everybody? Cool. So, how do I switch now from one file to another? Oh, there it is. So, let's look at the Kubernetes controller first. So just don't look at everything, but just see, this is the moment where Kubernetes controller actor receives a message asking to add a node. And then what follows here is really just using the Kubernetes API. If we don't have any workers at all at this point, we will create a new deployment. Remember the waiter. Create a new deployment using this fantastic Java API. And if we do have controller, which already spins up a worker when it's born, then we'll just ask Kubernetes to give us one more replica. That's it. Below, you'll find a case where it receives a remove node message, and we'll just ask Kubernetes via its API to remove one replica. There it is. If we look at how the master uses this, so the master here, I have built a big logic to decide how many jobs we are consuming at the moment and if it's enough or not. When it's not enough, there it is. Yeah, this is the case where we have too much power. Please remove a node. Maybe what's interesting to look at is also we're going to look at the worker, and we are going to look at the worker configuration. Yeah, so Akka cluster requires you to specify a few things. If you then run your applications inside a Docker container, you need to specify even more things, but it is doable. What I want you to look at especially is this. This is the key thing where we specify where the seed node is. And this will be the name of our actor system. And this one here is our DNS name. So here you could have, 1.3.2.4, but you want it to have fixed, as I said earlier. So we're going to give our seed node that DNS name. And then all of this comes together in the YAML file. The YAML file is the menu that I was talking to you about. Is the node that you send to the kitchen in order to have your orders delivered. And the YAML file is somewhere here. Yeah, there it is. So it looks verbose, I know, and there are ways to add templating in this, such as Helm. Maybe someone has used Helm charts before. But what we're doing here is we're asking for a deployment, specify a bunch of things about it. We are telling deployment which image, which Docker image to use to spin up this node, which this is what I called my image. We pass some environment variable. Let's see if there's something interesting. Yeah, we pass this thing, which we refer to later here. When we create this service, this is the point where we declare a DNS service. So the node that we just saw above, on top, will be reachable by this Akka master name. Yeah, YAML files are verbose and a bit painful to look at, but they work. So, and we're gonna, yeah, there it is. Anyway, time for some live/recorded demo. Kubernetes offer a command line interface, kubectl. In this case, it's already configured to look at my own account. So when I call this thing, Kubernetes kubectl get pods and deployments, this is exactly what is running on my cluster right now, which is nothing, right? So now we're going to use this command kubectl apply -f service.yaml. This is going to start the master, which will start to receive jobs from the input source, and then you will immediately see that it starts creating workers. Yeah, they're coming, container creating, running, and in a bit you should see that a worker is born to start processing. Oh, there it is. There's the first one coming up. So if you look at the names, this is the name that we've given it. This is something that Kubernetes adds to make a name unique and more difficult for us to read. It's creating more nodes, and I have actually created this very, very simple thing. Yeah. So here, basically the master is pushing down a WebSocket statistics about what's going on. For instance, what's the queue at the moment? How many workers do we have? What's the burn down rate? But this takes a while to go ahead, so what I have done is I have prepared a video for you guys, which goes much quicker. There it is. So here I'm doing the same steps I've done before. Master is created. Opening the WebSocket right there. there it is. So, the blue line is the queue of jobs that are waiting to be executed. And now it's growing because we don't have enough workers. The number of workers is the red line, is the little one. So now, see, there's been a little bump because the master created a new one. And as you can see, the queue is starting to ease down. The yellow line, it's actually the most important one, is our burn rate. So that means how many jobs are we burning with respect to how many are coming. And finally, the green line is how many jobs are coming in every window. So what's happening now? The master has created a lot of workers, but the queue has reduced in size, and so it killed one. And then it stabilizes around 0. So look at the bottom right. What I'm doing there is I'm increasing the rate. So the green line has gone up, because I'm now pushing more jobs to be executed. The queue has begun to grow again. And so our yellow line went above 0, which means we're receiving too much jobs. And so the master is creating new workers again. Same thing. The line is going to ease out a little bit and eventually get back down to 0. So now the yellow line is again below 0, which means we're burning more jobs that are coming, but we're happy with it because we have a long line. And as soon as the blue line reaches back towards 0, you will see the master killing mercilessly the workers. Someone has to do it. So the thing is, our goal here is to have the yellow line as close to 0 as possible, because that means that we're burning exactly as much as it's coming, which is, just the right amount concept that we described earlier. I think I am going to do another little experiment in a second. So here on the bottom right, I think I am going to set the rate to 1 message per second, while now it's 4 messages per second. And so if I do that, come on, Fabio. Then you will see that the green line drops to 1, and again, the master starts butchering workers like there's no tomorrow. Yep. Yeah. Oh my God, we have so many unused resources right now. Let's kill them all. Come on. Yeah, there you go. The yellow line is already going back towards 0. And so this is it for the demo. Now, a couple of, where were we? A couple of conclusions. Yeah. So what was for me the most important learning of this exercise? I have always been an application level guy, but what I really learned about this is that in reactive systems design, that means thinking about your application, but also about how you're going to deploy it, how you're going to run it. Are you going to use EC2 instances? Are you going to use Kubernetes? What I learned is really think about it beforehand, because this saves a lot of hassle later. When I developed my phone engine thing, I thought about scalability and elasticity, but didn't really build it in, which, I mean, in hindsight, it was a good thing, because I never really had 1 million users concurrently. But I had the plan, but it was like a cumbersome plan. And so think always about your infrastructure as you're building your app. Don't leave it for later. That was my biggest learning. And then another consideration I want to make here is actor messaging. Is that cool? Is that a thing? I have HTTP and WebSocket, so actor messaging, where does it sit? What's its place in the world? Of course, HTTP is ubiquitous. So if you have different services, maybe written in different languages, then HTTP is your way to go. But if you are using Akka already and your services are in Akka, well, actors have already built-in location transparency. Actor messages don't necessarily need to wait for a response. It's not a response. I mean, sometimes, yeah, like the guys earlier explained, you can wait for a response, but you don't need to. Not necessarily. And then again, if you're already using Akka, then why would make your system more complex by adding an HTTP library? And finally, one thing that was really cool for me to see at a previous conference, performance. HTTP has so much more overhead. Actor messaging works on TCP. I think you can choose to have it on UDP as well. HTTP, with all its headers and stuff, there's so much text being sent over the line that you probably don't need. This guy is a Dutch guy. This was at a conference in Amsterdam. He built this entire theme park with Legos, and it all moves. It all works together because each component has a little Raspberry Pi on it that runs a very tiny JVM on it. And so he was doing things like, when the train reaches the cow, ring a bell, and things like that. And it all worked. And this was all based on actor messaging. And he shared with us the comparison he'd made about the mean response time. The green is HTTP response time, whereas the blue one is the actors. And obviously, HTTP is a lot slower. So for cases like IoT, Internet of Things, maybe HTTP is, it's overkill. Right, I am practically done. The repository for the demo that you have seen is online on GitHub. There's 4 different projects: the master, the worker. There is a common project, which is basically the messages that are shared between the two. Maybe some logging functionality. And there is the stats visualizer, which is my super fancy front end that you have seen earlier. I suck at front end so badly. But there you go. Go ahead and check it out. I think it's quite nice to see the setup. And about the Holy Grail that we mentioned at the beginning. So is this solution really the Holy Grail? Well, for me personally, it kind of is. Again, with my projects in the past, I never used Kubernetes, and I am not a DevOps guy at all, but to learn how it works was easy. I'm not endorsing Google in any way, but I use Google Container Engine. There's others, like Azure and AWS recently also added one. But the Google Container Engine, the way it works, it's really easy. So if you don't want to spend too much time on it, I would recommend it. But then when, of course, we were talking about software development, right? So everybody should choose his own Holy Grail based on your situation. And maybe you remember the movie, how it ends. But yeah, that's up to you. And this is what I had. So thank you for your attention.
Thank you. So, time for questions.
First thing, where I work, I'm formally prohibited to work on front ends because mine are too ugly. So you're not the only one. And my question is, what about code upgrade? When I have a new version of the worker code, how do I switch it inside the cluster?
So my own application code. Yeah, Kubernetes has many more functionalities than what I've shown. One of them is about rolling upgrades. You can upload a new version of the pod and tell Kubernetes, spin up my class, spin up my new pod, my new service, and only when this new one is active, kill the other one. So this is taken into account. And I don't know exactly how to do that because I'm not an expert, but it's thought of.
Hi, my name is Michael. So I think if you use AWS or probably also Google and others, you can configure, when you configure your application, some kind of scale up, scale down rules, like if CPU exceeds something, then add a node, otherwise remove node and so on. And this seems like a quite similar programmatic way of doing that. So when should I use something like this versus just choosing a slider in AWS, or how do you think about that?
Yes, that's a great question. Indeed, Kubernetes has some features that let you set up some auto-scaling rules, principally about CPU usage. So if my pod has reached CPU usage of 90%, scale and give me a new pod, things like that. There is a plugin that works together with Prometheus that can let you specify more custom metrics, but it's a plugin. At the moment, it's not yet in the Kubernetes core. You should totally use this with actors when you need your own custom metrics. Maybe you don't want to wait for CPU usage to explode or memory to be filled, but you want, you decide that you only want 10 workers for each node. And then when you reach 10, you just spin up a new node. And Kubernetes wouldn't have any clue about that because Kubernetes doesn't know what's happening inside your pod. So yeah, excellent question. It really depends on your situation.
Anyone else? Okay, I'm going to shoot my question for you.
Whoa.
If I figure out correctly, you're kind of controlling the Kubernetes cluster from within the Akka cluster, right? Did you ever try the other way around, like trying to develop and design the Akka cluster solution totally independent from where, I mean, you were advising to take into account where you're going to deploy it. Did you ever try the other way around, like trying to be totally transparent of where you're going to deploy it and make Kubernetes and Akka clustering fit together?
In my Kubernetes journey, no, I haven't tried that. But then, I think you fall back to the case that Victor was mentioning earlier, where for auto-scaling up and down, you only rely on Kubernetes' own metrics without being able to control more granularly. But yeah, you can.
Okay, thank you. Anyone else? Great.
How does the resiliency go? I mean, if you actually kill the EC2 instance where the worker is running, what happens?
So if the instance where the worker is running goes down?
Yeah.
Yeah, unless you specify otherwise, Kubernetes will automatically restart it. Now, that opens the door to a nice issue with Akka cluster. Because when the worker goes down, Akka cluster marks this node as unreachable. And it has to wait for a certain time for it to be able to rejoin. So now this node spins up again, but Akka cluster says, hey, I marked you as unreachable. And so there is a little trouble there that it's good to take care of. Definitely.
Other questions? Okay, I guess that's all. Thank you again.